So hi, good evening, everyone. I welcome to this session. I'm Varun Sethi, and I'll be covering today's session. So session is about securing embedded systems. It's an overview. I'll be covering multiple. I'll be touching multiple topics here with respect to the security aspects of embedded systems, primarily looking at the edge devices. And each and every topic that I cover, there's a lot of scope in going in a lot of depth and learning more about it. So this is just tip of the iceberg, right? When you talk about security. Okay. Second. So brief introduction. Well, I am here at NXP, and I'm currently managing the MPU Linux infrastructure security team. This is part of the security technology group of the edge processing software R&D team. And as part of this, so we are actually looking at the various software security aspects with respect to the SoCs that are being developed by the edge processing business line. Okay, so quickly moving forward. So this is the agenda for today's presentation. So we start by looking at the various security threats that are quite real and exist that could impact the edge devices. And then we look at the hardware security capabilities, which can actually be used for countering these threats, right? And certainly these are security capabilities that we have on the NXP SoCs, and we work on enabling these capabilities so that our customers can actually build secure solutions on top of our hardware. After covering the hardware security capabilities, we will look at a brief look at Secure Boot. I think Secure Boot was covered once during the Campus Connect session. So we'll be briefly touching upon that and understanding what kind of threats are basically countered by Secure Boot. Why is it so important, right? Next, we will actually go into the Secure World software, understand first of all what is Secure World, right, and then look at the various software entities that actually function in the Secure World, and then the non-secure world, which is the normal world, right, where every application that not every application, but yeah, most of the applications that we use, right, and what most of the network applications, the ones that which we use for maybe communicating to any external server, right, where they're operating. So we look at the non-secure world software, understand the security capabilities there, and how the hardware, the security hardware capabilities come into picture in that particular scenario, and certainly the non-secure world is also leveraging some services from the secure world as well. And towards the end, we look at device management, right? We understand the relevance and importance of device management. And in that, we'll also look at how can we securely manage the updates for our hardware. And at the end, we have the conclusion, and based on whatever we learned during this presentation. Okay, here we get started. So security threats for the edge devices, right? Interesting. So here in this slide, so in this slide, this is my embedded device or edge device, right? And within this particular device, I have various different components. You have the CPU core, you have the boot ROM, which controls the overall system boot. Then you have the various other peripherals. Then you have the control system control, which has the clock clock, which controls the clocks for various peripherals. You have the reset control, you have the power control, right? Then you have maybe a static RAM sitting there within the SoC, and then Outside, you have the you could have a non-volatile memory, a flash, you have the dynamic RAM, right? So everything connected to the SoC. Now, if you look at these dialog boxes, right? So these are actually highlighting the security threats which can actually impact each of these components, the SoC components, right? Be it internal to the SoC, be it external to the SoC, right? And what is the goal of these security threats? What are they trying to do? So what their main intention is to disrupt the uh, the ongoing operation of this device, right? It should not be able to operate normally. And the second thing is to steal whatever secrets are associated with this particular device, right? So that's what is being targeted here, right? For instance, if you look at this one, right, if a power glitch attack, right? So the main objective here is that you want to bypass a particular execution flow, right? And for instance, if there is some kind of a check that you have introduced in the code for I mean, it could be any kind of a check to make your code more robust, right? But if due to this, right, it is very much possible to I mean, it could make your code or I mean the processor bypass that particular check. And then with respect to boot ROM, if the secure boot checks are violated, right, then you end up booting any unauthenticated image on the system. So basically, you lose the complete control of the system. With respect to communication, right? I mean, if anyone is trying to steal information based on whatever is coming out of the device, right? So they can manage to do that if your communication is not properly secured. So these are the basic security threats, right? Which we need to be aware of, and we need to understand uh, how these can be mitigated, right? Obviously, we are not going to go into depth of each of these and try and see how these are mitigated. But I mean, the goal of this presentation is to give an overview so that make everyone aware that these are the security threats that we need to be aware of, and we need to counter these threats. Okay, so we just looked at the security threats, and so now how do these become concerns for the IoT edge device deployment? So typically, if the IoT edge devices, right? So you have multiple devices which are deployed at various different locations. So if any particular device gets compromised, right, that doesn't mean that that is the odd one out. I mean, you are actually putting the entire set of devices or related devices at risk, right? So that brings in a large attack surface, right? You can actually impact multiple devices and maybe bring down an entire network of IoT edge devices, and that could impact the overall services that they are providing. It could certainly lead to some commercial theft where I mean, certainly you could have some proprietary data which is residing in the IoT edge devices. For instance, it could be a machine learning model. I mean, if you are basically collecting some data, doing some analytics, data analytics on that particular device, or it could be a medical device, right? Which is collecting your health information and doing some computation on based on that. Any particular model which is doing this, I mean, that particular if that gets compromised, that gets stolen, right? So that's actually a commercial theft that we are concerned about. Uh, and the information that is being collected by this device, if it gets compromised and it gets used in an improper manner, I mean, it's a case of espionage. Uh, Cost sensitive because the IoT edge devices are, I mean, you're actually deploying multiple devices. So, and they are actually handling sensitive information. So the trustworthiness of the device is very important, right? You have to ensure that you can trust this device with the information that is going through it or whatever information it is processing. If it is prone to attacks, if the information can be leaked or compromised, right, then that device is not fit to be, I mean, it cannot be used as an IoT edge device. And there is suppose, as I just mentioned, right, for the case of medical device, right, or maybe a smart watch, right, which is collecting, which has a significant amount of your health vitals with it. If the device gets compromised, it can, I mean, your information gets leaked, right? It can be used in any manner, right? You don't know how would that impact you. And certainly these devices are spread all over, and they are very, I mean, they're not always going to be physically monitored. I mean, they are just deployed in the open spaces, right? So they are always prone to physical attacks. An attacker may decide to just plug one of these devices and try to use brute force mechanisms to get information out of that. And because of so many potential threats, right? So the longevity of the devices, how I mean, robustly they can handle these particular security threats. The longevity of the devices is also a major a requirement, but it is at the same time a concern as well, like how well it can tolerate these specific threats. Okay. So quickly, I'll talk about the hardware security capabilities, right, which can, to an extent, counter these specific threats. Okay. Okay. So I'll just quickly cover these hardware security capabilities. So the goal is that we just saw the security threats, we just talked about them, and the security concerns associated with these threats. So hardware capabilities are very important here because they are a very important defense that we have to counter these specific threats. Okay, so this particular wheel here, it actually lists the various hardware security capabilities that can be leveraged for countering these threats. So we start with secure boot, which is an absolute must for ensuring that you have complete control of the device, right? That's why, and you're just booting something, some authenticated image, and not any given software image on your device, right? You have control of the device. Secure storage is also important here because in these devices, right, we talked a lot. I mean, at least I talked a lot about the data. So we looked at the proprietary information, proprietary code that you have running on these devices. So secure storage is very important, and plus you have, obviously you are actually also encrypting some amount of data. So the keys that are being used for encrypting, so you need to store these securely as well. Manufacturing protection. So these devices are deployed remotely, right? So these devices have to be provisioned with the OEM software images. They might have to be updated. An updated image might have to be passed onto these devices. So the manufacturing protection capability is there to ensure that and whatever OEM manufacturer the manufacturer wants to provision, right, that can be provisioned securely to a particular device. So there is a small example that I have in the coming slides, in which I'll try to highlight a very small use case, not in much detail. Then key protection, obviously, whatever data we have and whatever code that we have executing on these devices, right? So we are protecting it using the keys. I mean, these could be the asymmetric keys, these could be the symmetric keys. So we have to make sure that these do not get compromised. So key protection is quite important, and there are hardware capabilities, accelerators, which provide these capabilities where I mean where you are not able to get these secrets in plain. So that is the main objective, right? Because a secret has to remain a secret even if it is within the system. Then about physical attacks, right? So how do we actually deal with physical attacks? So that's where tamper detection comes into play. So tamper detection is, I mean, you have a hardware block and there are sensors associated which allow you to detect uh, any tampering that is targeting the device. And based on that detection, a particular corrective action can be taken, um, right? And to make sure that the device does not get compromised due to a physical attack. Secure debug. Now there would be some debug capabilities which are there on the SoC, right? And if you have an edge device, right? You, I mean, if there could be a need for debugging if there is any kind of failure, but then while debugging, you do not want uh, any debugger to be attached and having open access to the entire device memory or access to the device IP blocks, right? So you need a secure way to even connect the debugger to the device. So that's the capability that you get using the secure debug interface, right? And then we have the secure world versus non-secure world. Software execution. So this is basically a controlled by the CPU or the core privilege level. So secure, when we talk about the secure world, so this is actually a software running at a higher privilege level, and non-secure world is something which is running at a lower privilege level on the core, and you have certain services which are critical, some certain system critical resources and services which are being exposed by the secure world to be used by the non-secure world software. So all these capabilities are actually a must and very important if you want to build a trustworthy system, right? And certainly just having one particular capability is not enough, right? Because the range of attacks, right? We saw that there could be multi there could be many different attacks, many different components that could be targeting a particular system. So you need a uh, a holistic picture and a lot of different mechanisms to be able to take care of these attacks, right? So I mean, the system has to be designed in such a way that it should take into consideration the various different attacks that are possible, and certainly the mitigations or the mechanisms to counter that using these hardware mechanisms. Okay, let's move to the next slide. Okay, so in this slide, I mean, the focus is on the physical attacks and and how we can actually use the tamper detection to basically block the physical attacks from occurring. So here in the diagram, you can actually see that we have a security monitor block, which is getting the information from various different sensors from the cores. And I'm sorry. So at any indication of a fault or or just a second, let me have some water. Okay, so at any indication where the secure monitor sees that there is a potential physical attack that is targeting the system, right? It can take uh, a corrective action. So what are the corrective actions here? So first is that you transition the system to a fail-safe state. Second is that you want to protect all the possible, all the secrets or potential secrets that might be in in the transient state. It could be something that could be stored on the the SRAM or the DRAM, secrets which are available with the security hardware. So you want to basically, I think you I'm sorry. So you want to zeroize all the secrets. You don't want any of the secrets going out of the system. You don't want these secrets to be leaked, right? So you can basically zeroize everything, wipe whatever secret keys were stored within the security block, and make sure that even if the attacker tries to get hold of the physical access, I mean, gets physical access to the system, right? Still, it cannot get anything out of it, right? Because you have actually kind of purged all the secrets that you had in the system. So that's what the tamper detection does, right? It blocks the physical attacks. Even if the attacker has access to the system, it cannot get anything out of it because you've already destroyed the information. Okay. Okay, so moving to secure boot, right? So we talked about the hardware capabilities. So secure boot is also leveraging I mean, so whatever mechanisms that we have on the system, right? So they are software and hardware controlled, right? For the protection mechanisms. So what secure boot offers us? So secure boot, as we touched upon, right, in the previous few slides, secure boot ensures that you are always running a particular authenticated image, right? So a signed image. So this you have specific keys which are programmed into the hardware, and the image that is being booted onto the system, it is signed by a private key, a symmetric private key, and you have the associated public key which is available in the fuse, hardware fuse. But that is, when I say fuse, it's kind of a non-volatile memory that you have on the SoC. And so while booting, you are able to authenticate a particular image based on the information that is stored on the hardware, right? And you only are going to boot an authentic software, right, which has been verified. And very important that you are able to establish a known good state. That means you have kind of all the way from the starting from the boot ROM till the operating system. You know that these are these are the verified images. This is what is the known good non known good system state, right? Where if all the images are authentic, and this is what I had to boot, right? This is the best the system state that we need. Also, this is about when we say chain of trust, what do we mean actually? So the secure boot is not just booting a particular image, right? So when you come out of the reset, the boot ROM boots uh, it brings up the bootloader, then bootloader brings up the operating system. So the point is that you have to ensure that from starting till end, right, all the images that are booted, right, all have been verified. It's not just about verifying one image. You have to ensure that everything is verified, and that's what is the chain of trust. So the boot ROM trusts the bootloader trusts the operating system. So when you are actually controlling whatever is running on the system, right? So you cannot uh, so whatever images are booted, I mean, that is actually controlled by the device manufacturer and the device user. So it prevents the device from, I mean, you're not allowing any given image to boot, right? So that means that you cannot, I mean, you otherwise, if you're not following the secure boot process, right, then any person, if capable of booting any other image, could repurpose the system, right? So a booting anything else means, I mean, the system was supposed to perform a particular function, but now because the system is compromised, it's doing some other function. And obviously, you're not allowing the unauthorized software to run. So another important thing is that although you are actually fusing the keys into the system, right? But there is always a mechanism to revoke a particular key, right? So if an attacker somehow gets hold of some particular version of software which was signed with a particular key, right, and it tries to and that software is compromised, right? So if you are able to revoke that particular key, the attacker is going to fail. It will not He will not be able to run that particular software on the system. So that's how the key revocation come into play. So that's again a very important feature provided by Secure Boot. Okay, so I think I did cover it extensively in the previous slide, but so if I don't have secure boot, right? If I do not have secure boot, then I could end up being in any of these conditions, which is not what I want, right? So the system, I could have a hacked bootloader, I could have a hacked kernel which is booting on my system. When I have a hacked bootloader, it could actually boot up any kernel image, right? Because that means I've lost complete control of the system. So although the hardware, hardware is there, but now that hardware is not in my control. It can, because the any software is running on top of it, so that hardware is capable of doing anything, right? In any particular thing which is not in my control. This slide is just illustrating how the secure boot is working, right? So you have a code signing tool. All this is done kind of offline, right? You have an image which is fed to the code signing tool. You have a key which through which you are actually going to sign this. The signed image will have a particular header in place, right? So you are actually appending a header to this particular image. So now when you are going to boot that particular image on the system, right? So this is the on-chip ROM, the boot ROM, which gets the control when the system starts coming up. Refers to the hardware security fuses, right, where the keys are actually stored, and once it gets the key information, it will use that to verify the bootloader. So bootloader will have the information in its header that was appended by the code signing tool, and this the boot ROM is going to basically use this the fuse information to basically verify the image and the header, right, and make sure that we are booting an authentic piece of software. So once the bootloader comes up, right, it's going to you again refer to the hardware security fuses and verify the next level kernel, right? So what we have is that we have the on-chip ROM, which actually trusts the bootloader, right? This is a verified bootloader, and then the bootloader which trusts the kernel, which is again verified. So this is effectively the chain of trust that we were talking about in the previous few slides. Okay. Moving forward. Okay, so now let's look at the secure world software. Okay, what do we actually mean by the secure world? So as I had actually mentioned in again in the previous few slides where we were looking at the hardware capabilities, right? Hardware security capabilities. So again, secure world software. When we talk about secure world, so this is secure world is kind of a hardware capability where you have a way to differentiate between different different worlds, right? When we say secure world, this is secure world is a trusted world where I have certain trusted services which could be running. And it's kind of a, a basic component of the trusted compute base, right? Um, and you, so the what can we have running on the trust in the secure world? So on the ARM application course, ARM A course, right? So we have the trusted firmware ARM, and actually not just the ARM A course, but even the microcontrollers, right? You have the trusted firmware. So on the microcontrollers, you have the trusted firmware M, and on the application course, you have the trusted firmware A, trusted so over here, I'm referring to the trusted firmware for the ARM application core. So that is I mean, this is one reference implementation that we have for the secure world. I mean, you can always look at the trusted firmware implementation. If you search for that, I mean, you have a code repository that is available, and where it's an open source software, and you have a big community which is contributing to this. So, what is the goal of role that this trusted firmware ARM uh, component plays, right? So, when we talk about the secure world, right? So we want when we talk about trusted entities, right? So what do we actually mean by that? So what we want the trusted world to do is that there are, I mean, we talked about hardware security capabilities. We talked about a lot of hardware pieces which are there and which provide you security capabilities. But there has to be an entity which actually goes and sets up that security, right? I mean, so all the hardware blocks have to be controlled by some piece of software, and that's where the this trusted firmware comes in. So it is responsible for the platform security configuration, and there are certain resources which are basically which have to be shared between the secure world and the non-secure world. For instance, there are certain interrupts that interrupt controller configuration, which is some memory management configuration, which needs to be partitioned between the secure and the non-secure world. So that is the charter of this particular secure world software. And then if you, I mean, quickly let's recollect what we saw in the case of the tamper detection, right? So we had the secure state monitor. Again, that needs some configuration. So that is again done by this trusted world software. And then you have the trusted execution environment. We'll just look at it in the coming few slides. That's part of the secure world. So trusted execution environment, the charter of the trusted execution environment is primarily to provide some, uh, I mean, actually provide some secure services to the non-secure world. And this is so the trusted execution environment is again in a way the gateway to this trusted execution environment is via again through the trusted firmware. And then there are other some services which can be provided. For instance, certain power management services which are provided by the trusted firmware through an SMC call. SMC call is like a system call which is coming from the OS directly into the highest privilege level. And yes, so this is a very important thing. So we trust this entity, right? So the trust entity, and this the when I say trusted compute base, so this is uh, running at the highest privilege level, and this is kind of a very important trusted entity. I don't anticipate or expect this to be compromised. So then if that is the case, right? So there are certain restrictions as to what it can do. It doesn't have to. It cannot include too many services. If we put in a lot of different services into it, that would make it that would actually increase the vulnerabilities. I mean potential vulnerabilities, right? It could actually add. You can go and add vulnerabilities if you try to kind of bloat this code base. So it has to be minimal code base providing certain specific services. It cannot be doing a lot of things. It cannot have too many IP drivers in it. So that is a very important thing about this. Okay, so in this slide, this is basically the typical boot flow with the trusted firmware, right? So you have the boot ROM, which and the trusted firmware capabilities are actually divided between these two, the BL2 and BL3.1, right? So the boot ROM is going to basically authenticate and bring up the BL2 image. So this BL2 is something which is when it comes up the DDR is not initialized, so it's the responsibility of the DL2 image to basically initialize DDR. Once the DDR is initialized, then it's going to copy the BL31, the BL32, the bootloader, the kernel images into the DDR, right? And so it would load drivers for the boot devices, for instance, the flash, will validate this the BL31 image before starting this BL31, and it will take care of the platform security configuration. Now the BL31, when it comes up, it's going to basically load this BL32. This is the trusted execution environment, which is running at the secure EL1 level in the core. And so BL31 is responsible for providing any runtime services that need to be provided to the operating system are actually residing here in the BL31 image, and takes care of the platform security policies uh, and power management services through this PSA interface. And the other, I mean, the hardware RNG. So this is the random number generation functionality. So you have the security block, which is again, so there are certain capabilities that can be accessed only in the secure world. So that is controlled by the BL31 here. So BL31 would actually start BL32. Once this is done, then it actually brings up this BL33 or the bootloader, and then the bootloader would actually bring up the kernel. So this is the typical boot flow. Okay. So now we talk about the trusted execution environment. So the trusted execution environment, as we can see, this is within this box, right? So this is the trusted execution environment. On the left-hand side, we have the normal world. Here we have the secure world. And within the normal world, what you can see is that you have two different applications which are running on top of the operating system, and each application has a particular service requirement which is actually residing here in this area, which is controlled by the trusted execution environment, which is Opti trusted OS Opti, and it is also acting as a secure partition manager. When I say partition manager, because we are actually hosting two different services on top of this trusted OS, and then this partition manager has to make sure that each of these services which is running on top of it is isolated. So this service cannot access anything which is being I mean, the data or the code for this particular service. So they have to be isolated, and that's where I mean, it's not physical partitioning, but kind of logical partitioning has to be done. And plus, you will need hardware capabilities as well to make this partitioning more robust. So yeah. So essentially, like when we have this client app, which is this blue colored box, right? If it is looking for some crypto services, cryptographic services, which are hosted here. So it uses a particular FFA interface. This is a specification defined by ARM to access. Basically, it talks to the operating system. Operating system through the FFA interface talks to the trusted firmware. I mean, this would be an SMC call, which is landing in the trusted firmware. Trusted firmware gets the parameters from this SMC call. Okay, it understands it has to get the service from the trusted execution environment. It would pass the parameters. Again, these are FFA parameters, which are going to the trusted execution environment, and the trusted execution environment then actually connects to a particular service here, and then this service is performed in context of this application. And similarly, in this the green color box, right? You have the corresponding green color box here. So you have the storage service, secure storage service, which is available here. again hosted by the trusted execution environment. And here again the application is wanting to get the service from the trusted execution environment. Again, we have this FFA flow between the OS, trusted firmware, and the Opti, and which ends up all the way into the this particular service here. So in short, right, so when we look at the trusted execution environment, the main objective here is to be able to provide some secure services to the non-secure world. Okay. Okay, so we just covered the secure world. We understood the relevance there, right? But mostly whatever development or obviously we will be developing something for the secure world, but most of the applications which are going to be running are actually running in the non-secure world, and even the bootloader for that matter is not a trusted entity or a secure world entity. But yes, it is participating in the secure boot flow. It is responsible for authenticating and loading the OS image. And then we talked about the manufacturing protection, right? So although this is not a trusted entity, but just a small use case, right, on the bootload how the bootloader can actually play a role in the OEM provisioning, right? So obviously, like when when this the manufacturing protection flow that I'm showing here, it is being done in a trusted environment. Not we're not talking about the trusted or the non-trusted world here, but trusted environment where this device is getting manufactured, right? So so this is just an illustration, right? So so the goal is that we want to provision a particular OEM application on a device, right? On on an embedded edge device. So how do we do that in a secure manner, right? So uh, essentially, like I so what in this particular flow, I'm just trying to illustrate that. So there is a particular key. You'll have an encrypted image of the software that you want to be installed on the operating system, right? So that particular image would be encrypted using the key. I don't want the key to be accessible to the operating system. I just want the OS to be able to uh, decrypt the image that I'm providing, but without the OS knowing about the key. So what we do is that we provide the encrypted key to the bootloader, and then you have the manufacturing public key fuse, right? So basically, the key is encrypted using the manufacturing public key. So the bootloader can actually read this key and is capable of decrypting it. And once it is decrypted, so you have the security hardware. Right now, we are talking about key protection here, right? Although so these two steps, right, could be actually merged into one, where you can actually program the hardware in such a way where you can convert this into a secure the key into secure blob, right? Without basically getting this out in plain. But here that is not the case. What we do is that we decrypt it and then we actually pass it to the security hardware, which actually uh, converts it into a blob, which is kind of, I would say, it's the key is itself encrypted, and it can only be decrypted by the security hardware. It cannot be decrypted by without the security hardware. So once we have this blob is passed to the operating system, right? Now OS has the blob, but it does not know about this key which was provided to the bootloader. So now once the OS gets the blob, right, and it gets the encrypted application that the OEM wanted to provision or install on this particular hardware, right? It can use the security hardware, give it the blob, And this security hardware can actually then uh, decrypt that application using the blob without actually ever giving out the key in plain. Okay, so moving to the just covered about the bootloader and about Linux or the operating system, right? So in this case, we have Linux, right? So so if you look at the OS, right? So OS has these security capabilities actually spread across at these different layers. Like you have the applications, you have the libraries, and you have the Linux kernel subsystem. Um, so the application layer is actually responsible for end-to-end security. And as I mentioned, right, so whatever, I mean, most of the functionality that you'll be using, right, so those would be primarily hosted in the non-secure world, and you'll be using some applications for encrypting the data when you're actually trying to transport that data over the network, right? So the network connectivity is in the non-secure world, right? And here you have multiple different uh, libraries, middleware, which are being used by which would be used by any third-party applications, right? So whosoever wants to use the security capability in the non-secure world. And then you have the Linux security subsystem, right? And each of these entities which form the Linux security subsystem, right? They are providing the cryptographic functionalities. You have the network security component. You have the disk encryption capabilities. You have uh, the TLS capabilities, file system encryption. Right. So all these capabilities are being offered here in this subsystem. Then you have the integrity measurement architecture. So these are actually there to basically support the applications and plus also ensure the overall system security, right? And so that's what is the goal of the Linux security subsystem. Oh, the important thing here is that you have a lot of hardware capabilities, hardware security capabilities in the device, and these capabilities are being leveraged by the application layer and the Linux security subsystem layer, right? So for whatever functionality they are providing, right? And the goal is certainly you want robustness, you need security, and that is based on these hardware capabilities that are available here on the SoC. And so the application layer and the Linux security system subsystem layers are actually interacting with these drivers to basically get access to the the hardware security capabilities in the platform. Okay, so we have looked at the secure world, the non-secure world. Now let's come to this interesting topic, the device management. So, okay, so why do we need device management, right? So, I mean, you can see that you have so many plethora of devices, embedded devices uh, deployed for various different use cases. So one thing to note is that the devices are actually going through various different phases. I mean, there is you device gets manufactured, there's some to configure the device, and then finally there is a particular use case that each device is actually catering to. And once the device is being used, right? So there is certainly the device needs to be maintained, right? We saw I mean, there could be a need for updating the software uh, based on maybe some capability enhancements, fixes for certain security vulnerabilities and stuff, right? And finally, that device once is used and till the end, right? So it has to be decommissioned, or I mean the device may have to be. I mean, there could be an ownership transfer, right? You're transferring from one person to another, so the user of the device is changing, right? So all this is, I mean, that's how we actually define the life cycle, right? From manufacturing to final decommissioning of the device, right? So there are various different stages through which the device passes. And and we know, right? Each device uh, has I mean, a lot of software components. You have the firmware, you have different software services, right? And and each of these services that are being hosted by the device, the particular device, are actually uh, now mostly controlled via cloud, right? I mean, you could have different services which are running on a particular device, which are actually controlled through the cloud, right? For instance, if I take the case of uh, Alexa voice recognition, right? Uh, so in that case, right, although I think so you have that device lying somewhere in your house, you can give it various different commands. It will perform some actions, but finally the main brain behind that particular the voice recognition is actually sitting somewhere in the cloud, right? And without the network connectivity, it cannot do much, right? So cloud connectivity is very uh, is an integral part, right, for that particular edge device. And certainly managing the device, when you manage the device, you have to keep a track of the device ID that is uh, actually tied to the physical chip that was used for the device manufacturing. And then you're actually tying the device to a particular user and particular service as well. So all that has to be managed. You need to have a record that this particular device is being given to this particular user and providing X service, right? So that is again part of the device management. And once and now, as we have actually seen, right, the IoT edge devices, right? So they are actually an integral part of our day-to-day life, and they are actually knowingly, unknowingly, right? For us, at least, the device is collecting a lot of information, and it could be about the health, it could be about my personal preferences and stuff. So the thing is that there are a lot of uh, legal regulations which define how this particular information that is being collected. First of all, what all information can be collected, how that information can be used, and once say the device is being decommissioned, right? So that information has to be erased, or if the device ownership is being transferred. So we have to make sure that the device is wiped off clean of whatever information was collected. So you have these regulations by EU, the General Data Protection Regulation. Then you have the CPRA from the US, which dictate these particular things with respect to the edge device. And so we have to make sure that all these things are uh, I mean, whatever information is collected, how it is used, how the device is decommissioned is as per the regulations. Otherwise you cannot have that edge device performing that function. Yeah. So so the device management is, and that's the reason that device management is quite important. It's critical. Okay. So if you look at this figure, right, we talked about in the previous slide that a device goes through a particular life cycle, right? So that's what is basically illustrated here. I mean, you have the manufacturing. So NXP is providing the chip to the OEM. OEM is actually manufacturing the device, but both NXP and the OEM are actually provisioning some certain keys into into the device, right? Which would be later on used for the device onboarding and for the services to be installed onto the device, right? But You have the manufacturing being done by an untrusted entity, which is basically maybe contracted by the OEM, right? So the manufacturing entity manufactures the device. So you finally have this particular IoT device available now, right? And once this device is available based on the keys that were programmed, it can the device onboarding happens, which is again controlled by the cloud OEM cloud, right? Now, now what could go wrong here? Um, any guesses? Anything that we are missing? I know we are almost towards the end of the presentation, but any guesses like what could be going wrong here?
Security layer is not proper.
I'm sorry.
Means we are not assuring the security between the packets, like between the movement of the data packets.
Okay, so this is not data packet movement, but yeah, this data packet movement with whatever is happening, I mean, that's where the keys are coming into play. So that would be there.
So
But now
NXP keys won't be there, right?
the NXP keys are also there. NXP keys are there. But yeah, okay. The point is that this manufacturer is untrusted, right? And you are handing over the device for manufacturing to this particular entity. We talked about physical attacks, right? We saw, I mean, we discussed that there are physical attacks which are possible on the device, brute force attacks, right? Uh, I mean, you do not know, I mean, what this manufacturer can do because you do not trust it. It may try to get the secrets from your device through brute force and try to maybe create another device which is not using the NXP chip and try to showcase this device to the device management cloud as something which the OEM wanted, right? I mean, that is a possibility, although not easy, but certainly that could be a possibility, right? And I mean, it could end up, it could be using some different chip, which is not even NXP, right? So how do we address that? Okay, so that's where this NXP trust provisioning and the edgelock 2 Go comes into play. edgelock 2 Go is a cloud-based service which is provided by NXP. Now, the basic goal here is that I want to authenticate this device. I want to make sure that this is the device which comes out, the device that comes out of the manufacturing facility, something which I wanted, right? Whatever the OEM wanted. So what happens here is that when we are provisioning these keys, right? So I'm also sending this to an XP Trust Provisioning server, which is actually then talking to the edgelock to go service in the cloud, right? So now when this device comes out, right, before it can actually get onboarded, first we authenticate this device, right? And the keys, so whatever information is stored here, right, in the edgelock to go cloud, right? So here we have the keys connected to the device ID, the NXP device ID, right? So if the device is something which is not something which I expected, that it will fail the authentication here and the device will not get onboarded. Okay, so only once the device gets authenticated, this onboarding is going to happen. Right? Once the edgelock to go service authenticates his device, only then device onboarding happens, and you have the this device provisioned with the OEM software. And then you have these OEM services also, which would get pushed to this particular device. And the device, certainly the device management also looks at the device monitoring, pushing the platform updates, plus the app services. There could be multiple services that this device could be offering. and also keeps a track of the keys and the certificates which are provisioned, which were provisioned in the device, and if these need to be updated, it will these would be updated here. And finally, the device decommissioning. So all that is part of this device lifecycle management that we do. If you look at what is there in the what we have in the device, we have the so the device again, like we talked about this, the secure world, non-secure world, and various different drivers, hardware capabilities, right? So this particular device will have OEM applications. It will have third-party app platform, third-party applications running here. You'll have certain secure world services which should be there in the device, right? So all that we talked about, right? That's all comes into play, right? When device is, I mean, when you actually manufacture the device and the device is running, is there in the real world, right? Okay. Moving forward.